Hi, it's me again. As you, I'm sure have noticed, I'm in lab, and I'm going to say this again, even though it didn't happen last time. I was pretty surprised, but there's a very good chance the lights will just go off right there. Motion detecting and on a timer, so don't be startled if it suddenly gets dark. I'm very used to it by now. So anyway, in this video, we're going to talk about rotational kinetic energy, and as we'll see, this has a lot to do with things like objects rolling, say like wheels or, balls, things like that, things that have some kind of sort of circular symmetry to them. And so what I want to do is I want to get started with a meme, a dank physics meme, if you will. And so I think that this is this is on a t-shirt that like Spider-Man wore in one of the Marvel movies, if I'm not mistaken. I think it was the first Spider-Man movie, but I don't know, it's kind of funny, right? And looking at this, you might be thinking, well, like, wow, this looks complicated. And it actually can get kind of complicated. But I'm going to do my best to keep it simple and not really go into any unnecessary details with this. So let's begin by thinking about, we're going to do a little thought experiment, I guess. I don't really know if it's a thought experiment, but that's what I'm going to call it. And what I want you to do is consider a point mass undergoing uniform circular motion. Let's see, with tangential speed v through a circle of radius r. So we know that the translational kinetic energy of the point mass can be written as k, right? K equals 1/2 mv squared. So nothing surprising there, right? Remember that this is the tangential velocity or speed, and it always points, well, tangentially to the circle, right? So let's look at this in another light. Let's say that, but using the idea of moment of inertia, remember this was defined to be this, like for a collection of point masses, say the mass times its perpendicular distance from the center of the circle squared, right? We just add a bunch of terms like that up to get a moment of inertia for a collection of particles. But for one, it's just going to be this, which for the point mass is, it doesn't need to be a sum now, right? Because it's just one point mass. And we know that its distance from the center of the circle is big R. So we can use this to solve, why are you doing that? For the mass in terms of the moment of inertia and the radius. And this would just be m is I over r squared, right? And we also can go back and forth between the tangential velocity and the angular velocity, or I guess I should say tangential speed and angular speed, right? Because we don't know which way this thing is moving, and it doesn't really matter. So let's recall that we can write the tangential speed as r omega, and this, of course, implies that v squared equals r squared omega squared, right? So then what we have is we can write our kinetic energy, and I'm gonna call it k sub t now, because we're thinking about, well, first we're thinking about the translational kinetic energy, right, which is this. But let's make these substitutions, right? Let's substitute in for the mass and the speed. So the mass becomes big I over big R squared. and the speed becomes r squared omega squared. And this just works out to be 1/2 big I omega squared. And this is defined to be rotational kinetic energy. Okay, and that's largely what we're going to be talking about in this video. And so I want to just say right off the bat that this thing that we're thinking about is a point mass, right? And a point mass, by definition, cannot spin about its own axis because it has no extension in space, right? It just occupies a single point. So for a point mass, we see that the translational kinetic energy can simply be expressed as a rotational kinetic energy. But pretty much all the time for any sort of real life object we might be thinking about, it will have, or I should say it can have, both a translational kinetic energy and a rotational kinetic energy separately, right? So hopefully that's not too confusing. We'll see some examples of that as we move through this topic. But anyway, the idea is that, let me say, for an object that is spinning about its own axis and translating through space. And remember, when we say translating, I think this idea of spinning is probably pretty clear to everybody, but remember when we say translating, it's like, you know, at one instant its center of mass might be at say one xy position, and then later its center of mass is at a different xy position, and that's all we mean by translating. So let's see here. For an object that is spinning about its own axis and translating through space. So, okay, so you can imagine, right, for those of you who are into sports, the quarterback during a basketball game kicking the puck with a perfect spiral, right? Maybe this helps some of you. But we can write its total kinetic energy as, and let me do it like this. I'm going to say K. Okay, so now I'm just going to say K without a subscript is the total kinetic energy. And the translational kinetic energy is going to be a big K with a T subscript, and the rotational kinetic energy is going to be a big K with an R subscript. So we could write this as, we just fill this in. It's 1/2 mv squared plus 1/2 I omega squared. And notice that this is very similar to what we've been doing so far, where we just take our m's and make them i's, we take our v's and make them omegas, and we're, you know, pretty much good to go. So let me see something. Okay, I'm just going to comment on this a little bit. I'm going to say here v is the speed with which the object's center of mass is moving, and this is sometimes written as v sub cm, but I'll usually just write a v with no subscript. And omega is the rate at which it's rotating, right? Just its angular speed. Okay, cool. And I'm not going to do the dimensional analysis here because, well, largely because of this, right? We just saw that we can take the mass and the tangential speed, and using the idea of moment of inertia and angular speed, make a substitution. And so this is equivalent, right? At least in terms of the dimensions. I mean, always in terms of the dimensions, it'll be equivalent. So this is going to have the same dimensions as energy, and it's going to have units of joules, right? In as much as this has units of joules. Okay, so I also just want to say that if the radius of the object is constant, it pretty much always will be, right? And there are no external torques, the rotational kinetic energy will be constant, right? And this is just extending conservation of energy to objects that are rotating now. Okay, cool. So then let's talk about the relationship between the center of mass velocity and the angular velocity. And now I found like an image online that I kind of like, so I'm going to just copy and paste that in here. And we'll break it down. Well, we're actually not going to go into a lot of detail with this because this can be a little bit complicated, and I'll tell you what the point is after maybe I talk about this just a little bit. But the big idea is, imagine like a hoop, right? Like a wheel maybe, or a ring or something. And this image, this part of the image here on the left, is what it would look like if it's just translating, right? And in this case, every point on the ring, I'm just going to call it a ring to be definite, is moving with the same velocity, right? Because it's a rigid object, and you know, you could just make little marks like on it with a Sharpie, say, and if you watched a movie of this thing moving, right, it's not rotating, it's just moving. Okay. You would just see these points move probably in like a straight line, as suggested in the image here at least. Then you want to think about what it looks like when this thing spins, right? When it rotates. And for this middle part of the image, we're just imagining that it's stationary. It's just like maybe levitating in space, just spinning, right? And now it's like each of these points just has, at some instant, its tangential velocity vector looks like this, right? Or like this, or like this. And that's just by definition of the tangential velocity. But then when you combine these two motions, right? So now you have something that's translating and rotating. These points have velocity vectors that are given by the vector sum of the other two cases, right? So you could see, for instance, that like this makes a 45-degree angle. This is double the velocity of the center of mass. This is actually instantaneously at rest with respect to the ground. And maybe you can see that if you think about adding this vector to this vector, right? And so this is, just to reiterate, something that is translating and rotating, right? And that's what like the wheel of a car does when you drive, right? Its center of mass is moving, but it's also spinning. Now, let me see here. So the point of this is that this is kind of complicated, okay? But if we can just remember that for an object that is rolling without slipping, and the equation here is just going to be that the speed of the center of mass is given by the radius of the object times its angular speed. And this would be, we could call this the no slip condition, rolling without slipping. Anyway, if we can remember this, we're going to be okay, right? We'll be just fine. Okay. So let's look at an example of this then. And note that this tells us, right, that we can figure out what omega is from the center of mass speed. So this example, imagine you're riding your unicycle, right, along flat ground at constant speed, v equals 5 meters per second. If the total mass of the unicycle is big M, which is 5 kilograms, and the wheel has a mass of 1 kilogram and a radius of 0.3 meters, then we want to solve for the total kinetic energy of the unicycle. Now, this mass here, this includes the mass of the wheel, right? So the total, just to stress this, the total mass of the unicycle, including its wheel, is 5 kilograms. But we know that the mass of the wheel is 1 kilogram. So let's see what we end up getting here. Okay. So the translational kinetic energy is given by, and we'll call this case of T as our convention dictates, and it's just going to be 1/2 times the total mass, right? Because remember, if the frame of the unicycle is translating at 5 meters per second, then so is the center of mass of the wheel, right? And so this is just, you know, something you probably could have told me like a week or two ago, right? It's just 1/2 big M V squared. But the wheel is also rotating at a rate of omega, which equals V over big R, right? Just from this, just rearranging this. And so it has rotational kinetic energy. Case of R, right, by our convention for the notation. And it's just 1/2 big I omega squared. Now, for a wheel or like a tire, especially like a bike or unicycle tire, we can probably just approximate that as a hoop or a ring, right? So that's just going to be mr squared for the moment of inertia. And then omega, we said, was V over big R, and we have to remember to square this. And so we find that this works out to be 1/2 little m V squared upon doing the simplifications, right? So then the total kinetic energy of the unicycle is, let's say, K equals k sub T plus k sub R, which is 1/2 big M V squared plus 1/2 little m V squared. And we could simplify this if we were feeling fancy. We could write something like this. And that's it, right? And so remember the example, right? The very, you know, general, simple example we started with this. We started this video with had that the translational kinetic energy and the rotational kinetic energy were equivalent, and we could just express them different ways, right? But notice in this example, now we have something that has a translational kinetic energy and a rotational kinetic energy. And so the translational kinetic energy and the rotational kinetic energy are not equal, right? I just wanted to stress that. And that's it. You know, you go through and crunch the numbers here if you wanted to. I didn't do it. I don't know what you'll find, but you'll get something, right? Definitely get a number out of that. Okay, let's look at another example then. This is a pretty common one, and I think that'll have you do something like this on your homework, but maybe go into a little more detail. Okay, so you place a ball of mass 0.15 kilograms and radius 0.03 meters at the top of a slide of height 5 meters at a playground. So assuming that it rolls without slipping, what is the ball's translational and angular speed at the bottom? So we're going to do this with conservation of energy, right? And we'll see how now we can kind of adapt conservation of energy to include things that are rotating. So let me say the initial mechanical energy of the ball is simply the gravitational potential energy. And this would just be, we'll call it E naught. This is just mg big H, right? Because it's like you place the ball at the top of the slide and you set it down very gently so it's not spinning and it has no initial translational velocity. Now I need to be much more careful when I just start saying words. Okay. So then, thinking about what happens here, right, in real life, you know that you set it there, it's going to start to roll, and then it's going to eventually wind up at the bottom of the slide. So let's say, but its final mechanical energy, and this is if we set the bottom of the slide to be at y equals 0, which I think is a very sensible choice, is a combination of the translational and rotational kinetic energies. So what we can do here is we can start out by writing just E equals 1/2 mv squared plus 1/2 I omega squared. And then let's just kind of take this down line by line and fill it in. We can just solve for the translational speed, because once we have that, it's a very simple matter to get the angular speed, but we could also do it the other way. I'm going to do it this way though. So nothing changes about the first term here, but now we have to fill in the second term. We have to say, okay, 1/2. Now the moment of inertia for a ball, right? I had like a lacrosse ball in mind here. That is obviously solid, right? It's not empty inside, so it's not like a spherical shell. So the moment of inertia for a solid ball would be 2/5 m r squared. And then over here, we just say from the no slip condition that omega equals v over r, and then we square that. Let's keep going. So then we have 1/2 m v squared. We see that in the second term, the r squared should cancel out, right? And so we wind up with plus 2/10 mv squared. And then we can finally go through, well, not finally, because we're not done with the problem yet, but we can combine these. We can say, well, 1/2 is just 5/10, right? Plus 2/10. And so this is 7/10 mv squared for our final mechanical energy. Okay. So equating the initial and final mechanical energy, we find, and I'm going to give you the result here, and you can go through and do the algebra to convince yourself that this is true, and I'm not lying to you, but I wouldn't lie to you. So we should find something like this. It's 10 GH over 7 all under the square root. And remember that from the no slip condition, right, that this equals r omega. And so we want omega, we just divide both sides by r. And the way that I would do this is I would pull the r under the square root, but when you do that, you have to remember to square it, right? But this way you get, a nice expression that has everything under the square root. And yeah, and that's that. If you want to work this out, you should find that obviously v has units of meters per second, and then omega has units of 1 over seconds, right? Because remember, the radian is not kind of like a real unit. Okay, cool. So I had a video I wanted to show you now before we move on, and this is a classic demonstration that's done in intro physics classes, where essentially the instructor will just take some objects and roll them down a ramp, and it kind of gives you maybe an idea of how the mass and how the radius and moment of inertia and things like that affect how quickly these objects reach the bottom of the ramp. And I'm not going to say too much about this because I do want you to do something like this for your next homework assignment, but let's just watch this and maybe make a few comments as we do. So here we have two disks that have basically the different mass but same radius, right? You see, okay, cool, they reach the bottom at approximately the same time. And those two, right, so let me pause it actually, because those two had different masses and different radii. and it looks like they essentially reach the bottom of the ramp at the same time, right? So that's kind of interesting. And then here what he's going to do is he's going to take a disk and a hoop that have different masses, but it looks like same radii. And let's see what happens here. Okay, so the disk reaches the bottom first. And then now, these are two hoops, but the moments of inertia here will be different, right? Because there's this little like crossbar on one of them. So let's see what happens here. So it kind of seems like the moment of inertia is what's really going to determine, you know, which object goes or gets to the bottom of the ramp first. So now this last one, let me just make sure. Okay, so it looks like here one is like a solid disk, and then the other maybe has a hole in it. Let's see, and they have the same mass. But they would obviously have different moments of inertia, right? Because their distribution of mass is different. So that's a little food for thought, and like I said, I will have you work an example like that, or work a problem like that on your next homework assignment. Okay, so we need to talk a little bit about work and energy in the rotational case, right? And I want to do another very general example here. So first, talking about rotational work, what I want to say is consider a uniform disk of radius big R. If a constant force, and we'll call this big F, is applied tangentially to the edge of the disk, then the corresponding torque is, and we could just write tau equals RF. And I want to show you what I mean by this, just in case it's not clear, so give me a quick second here while I bring the whiteboard up. So what we have in mind here, and this will be very quick because we don't really need to say that much about it, but it's like so for some reason it's like when I touch it the first time, it will interpret that as like me trying to write something, but then after I reselect, use only the Apple Pencil, it doesn't do that. I don't know, it's very weird. See, now I'm touching it, it doesn't draw anything. Anyway, so the top view, right, if this is my disk, when I say the force is applied tangentially, I mean like, you know, it's just applied, so it's kind of like this. And another way of saying this would be that it makes a 90-degree angle with a line we could draw for the radius. And that's it, right? So let me move this over. Okay, so anyway, the corresponding torque is RF because the angle between the position vector and the force vector would be 90 degrees, right? And sine of 90 is 1, so the magnitude is just this. Okay. So let's say that this acts over an angular displacement of delta theta. So we want to remember this idea of arc length. So remember, we can use the idea of arc length to express the angular displacement as, and well, the arc length formula was just that the arc length is given by the radius times the angle, right? And so this tells us that we can write that delta theta is just S over big R. Okay, so then let's take the product. Taking the product, and we want to multiply tau and delta theta. we find, so we said that tau was RF, right? And delta theta is S over R. And this just works out to be Fs. And this is a work, right? It's just a force times the displacement. Or a distance, I should say. And this is what we'll call the rotational work. Okay. So this means, so we can define rotational work done by a given torque. Okay, I can spell. To be this. Cool. So then we want to think about what the rotational work energy theorem might look like. And it's probably going to look exactly as you would expect, right? Because we now have this idea of rotational kinetic energy and the work done by a torque. So what I will say is that the preceding analysis suggests that we can adapt the work energy theorem to the rotational case. And this looks like delta K rotational, and remember this is just 1/2 I omega squared minus 1/2 I omega naught squared. And this is going to be, write this like this, the net rotational work. Maybe like that. And that's it. So we're going to look at an example, but I want to show you a video first to sort of motivate the example here. And I don't know, maybe you've seen this before, but there's some guy making a pot, right? And so the clay spins around on this little wheel, and you know, whoever's making the pot kind of shapes it the way they want it. But see, the cat is, you know, helping out here, right? They're such helpful creatures. I don't know. I think this is funny. Yeah. So there you go. Okay. So we're going to do an example based on this. Okay, so let's assume the pot has a mass of 1/2 kilogram, and the radius is pretty small. It's like 5 centimeters, so let's say it's about 0.05 meters, and it's spinning at a rate of omega naught equals 30 radians per second. We can loosely approximate the pot as a hollow cylinder, so basically we approximate it as a ring, right? Because remember that our moments of inertia, our formulas for the moments of inertia of common objects include the moment of inertia for a ring, and there's no mention of the, let's say, like the height of the ring in that formula. And if you're not sure why that is, that would be a good thing to ask me about during the weekly meeting or office hours or an email, however you want to do it. Anyway, so let's say the coefficient of friction between the cat's paw and the clay is mu sub k equals 0.3. And the cat applies a very small force, right, of 1/2 Newton, and holds its paw on the pot for an angular displacement of 4 pi radians. We want to solve for the final speed of the pot. And so we just do this with the rotational work energy theorem. And let's see what that looks like. So we first have to solve for the torque that the cat exerts on the pot. And so I am going to bring the tablet up again because I just want to make sure that everybody's clear on how this works. But let's think about the top view of the pot, like that. And so maybe it's spinning, we're not told, but let's just say that it's spinning counterclockwise. And so when the cat presses on the pot, right, it applies a force that maybe looks like this. And what that means then is that now we're going to think about the cat's paw, right? There's a force applied on the cat's paw that looks like this, and I'll call this F prime, just because we know will have the same magnitude as the other force, but it's not the same force, right? Because it points in the opposite direction. Or I call it negative F2, but this is fine. But this is a contact force, a normal force, right? And so we can think of this as our normal force when we calculate the friction between the paw and the clay. And I just want to note that the friction force on the pot would point like this probably, so as to slow down its angular speed, essentially. Okay, so I wanted to make sure that that picture was hopefully clear in everybody's mind. And so let's just say then that this is given by, and tau equals R times the friction force, right? Because remember, torque is the distance from the axis of rotation to the point of application of the force, and the distance is R. The force being applied is a kinetic friction force, and so we could write this as R times mu sub k F, right, where F is the force that the cat applies on the pot and also that the pot applies on the cat. And then we could write that this is just mu sub k R F. So that's our torque, and it's the only torque in this example. Okay, so then the rotational work done, this is actually the net rotational work, right? Because we just said that there was no other torque acting on this thing. So the net rotational work done is, I'll write it like this, oops, R, and this is just going to be generally, it's going to be tau times delta theta, but specifically in this case it's going to be negative mu sub k R F delta theta. And you might be wondering about the negative sign here, and that comes back to the picture, right? Where this is rotating counterclockwise, and the torque associated with this force is going to tend to make it rotate clockwise, right? And so we just have to remember to be careful with our signs. Okay, so there's that. Then we just fill this in basically, right? Let me say thus, the rotational work energy theorem gives, and I'll write it out generally first. It's just going to be, recall, it's going to be 1/2 I omega squared minus 1/2 I omega naught squared, and this equals the rotational work. And now we plug this, we fill it in, we say, okay, well 1/2, that's just a numerical constant. We said we were going to model the pot as a hollow cylinder, which means its moment of inertia is just mr squared. And then omega squared is what we want to solve for. And then minus basically the exact same term, except this is now omega naught squared. And then we had that the rotational work done was negative mu k, big R, big F, delta theta. Okay, so it's just a matter of solving this then for omega, right? And I'll probably have Mathematica do that for me. Because the algebra is a little tedious. And that's not the point of this class, right? Even though it might feel like doing algebra is the point of this class sometimes. But let me just see what we get. Okay, so I want Mathematica to solve 1/2 times m times r squared times omegas. Oh, why are you doing this to me? Oh my god, okay. It's annoying. Why are you like this? Okay, we're gonna improvise. I'm gonna use W for omega, even though this is something you should never do. Minus 1/2 times m times r squared, and then I'll use a big W for omega naught, I guess. Oh, this is painful. Equals, and then I'm gonna call, will it let me do, no, it's not let me do the symbols. Okay, so I'm gonna call mu, I'm gonna call it u. R and F can stay as they are. And let's say that theta is just, oh, this is awful. It's just O. Alright. I don't like to see it if any of you don't like this. So anyway, we want to solve for big W because that is what we called omega naught. Oh my god, don't make me do this by hand, please. It shouldn't be taking this long. Okay, cool. So this would be our expression. So let me just write this out in proper. Oh, wait a minute though. Oh no, I wanted to solve for, I apologize. I wanted to solve for a little w. That's why that didn't look right. There we go. Okay. So this is going to be, we'll have everything under the square root actually. And it should be mr omega naught squared minus mu sub k, well, let's put the 2 in, minus 2 mu sub k f delta theta over mr. Let me just double check this, make sure I translated it correctly. That's 2 mu sub k. Okay, I think that looks good. So you could plug the numbers in here and see what you get if you're interested in that, but it, obviously we would expect, sort of intuitively, right, that the angular speed should decrease. That's what physics tells us. And we would just want to go through and make sure that the math confirms that, right? And it seems like it will, right? Because of the minus sign here. Okay, that's it for this. Miraculously, I was actually able to keep this fairly short. You'll get some more practice with these ideas on the homework assignment, and I will try to guide you through it very gently, so hopefully it's not terribly painful for anybody. As always, reach out if you need anything, any questions, concerns, comments, let me know. Otherwise, I'll see you in the next video.